explainer. We are jumping right into the physical world of matter today. Because, if you've ever stopped to wonder how scientists actually untangle all those complex, mixed up substances around us, well, you're in the right place. We're going to break down what everything is actually made of, how things mix together, and most importantly, the really cool ways we can pull them back apart. Here's our roadmap for today. We're covering 1. The fundamentals of matter. 2. Homogeneous versus heterogeneous mixtures. 3. Unmixing homogeneous mixtures. 4. Separating heterogeneous liquids. And finally, 5. The sublimation shortcut. Let's get into it.
All right, Section 1, the fundamentals of matter. What exactly is everything?
I want you to take a second and just look at the objects around you right now. Maybe it's a glass of water on your desk, the metal of your laptop, or honestly, just the air you're breathing. Almost everything you're interacting with isn't just one pure thing. It's a blend, a complex and very often completely invisible blend of different components. So the big question is, how do we untangle them? Well, to answer that, we've got to start with the basics. Matter is literally anything that occupies space, so it has volume and has mass. And the absolutely crucial thing to remember here is that it's all built from tiny particles. Now, depending on how tightly packed those little particles are, matter takes on one of 3 states: solid, liquid, or gas. Think about an ice cube, right? The particles are packed super tight, but if you add some heat, it melts into liquid water. Boil that water, it vaporizes into a gas. Cool it back down, it condenses back into a liquid. Basically, temperature is the master key that transforms matter from one state to another. Moving right along to Section 2, homogeneous versus heterogeneous mixtures, understanding mixtures. So when substances combine, they generally fall into one of 2 buckets. On one side, we have homogeneous mixtures. These are completely uniform. Think of a perfectly stirred glass of lemonade, or alloys like bronze and steel. Every single drop, every single slice is exactly the same throughout. Then on the other side, we have heterogeneous mixtures. These are non-uniform. If you scoop up a glass of muddy water, you can actually see the dirt floating around in there. It's definitely not perfectly blended. But things get really interesting when we break down these mixtures by the actual size of their particles. A true solution, like salt completely dissolved in water, has particles smaller than a single nanometer. That is incredibly tiny. They are entirely invisible and they never settle at the bottom. A suspension, like our muddy water from a second ago, has large particles, over 1,000 nanometers. You can easily see them, and if you just leave the glass alone, gravity is going to pull all that mud right to the bottom. But sitting right there in the middle is the tricky one: colloids. Things like milk or blood. Now, to the naked eye, milk looks completely uniform, just like a homogeneous solution. But microscopically, the particles are just large enough that it's actually a heterogeneous mixture, even though those particles stubbornly refuse to settle down. Okay, so if it looks uniform, how do we actually prove a colloid isn't a true solution? We use light. This is called the Tyndall effect. If you shine a laser pointer through a true salt solution, the particles are so ridiculously small they don't do anything. The light just passes through invisibly. But shine that same light through a colloid or a suspension, and the particles are big enough to literally scatter the light, making the actual beam visible. You've definitely seen this in real life. Think of being in a dusty stadium at night under the floodlights, or seeing sunlight slicing through the morning mist in a dark forest. That visible, glowing path of light, that is the Tyndall effect in action. Now, before we start pulling things apart, there's one more golden rule we need to know. If you're dissolving, say, sugar into water, eventually that water is going to tap out and refuse to take any more. It becomes what we call a saturated solution. But, and this is a big but, if you turn up the heat, the water magically unlocks the capacity to absorb even more sugar. Solubility is highly dependent on temperature, and as you're going to see in a minute, we can absolutely use this little physics hack to our advantage. All right, Section 3, unmixing homogeneous mixtures, separating the invisible. Let's kick this off with crystallization. Remember how heat allows a liquid to hold more solute? Well, let's say we heat up some water and pack it completely full of dissolved copper sulfate until it's totally saturated. We filter it so it's perfectly clean, but then we take away the heat. We just let the solution cool down nice and slow. As the temperature drops, the water naturally loses its ability to hold all that dissolved copper sulfate, so the extra particles literally have nowhere to go. They're forced to eject themselves from the liquid, and as they do, they automatically arrange into these perfect regular geometric patterns. The end result? Absolutely gorgeous, shiny blue crystals just sitting there in the beaker. It is basically magic, but, science. But wait, what if we don't have a solid dissolved in a liquid? What if we're dealing with two perfectly blended liquids that readily mix together? Take acetone and water, for example. When mixed, they look absolutely identical. You can't filter them, you definitely can't crystallize them. So how on earth do we pull them apart?
The answer is distillation. We exploit their different boiling points. Acetone boils at just 56 degrees Celsius, whereas water, as we know, boils at 100 degrees. So we very gently heat the mixture right up to 56 degrees. The acetone hits its boiling point and turns into a vapor, while the water just sits there, perfectly happy as a liquid. That acetone vapor rises up and travels into a specialized tube called a condenser, which is essentially wrapped in a jacket of cold water. Once that hot vapor hits the cold temperature of the condenser, it condenses back down into a liquid, dripping into a totally separate flask. And just like that, you've got pure acetone in one flask and perfectly pure water in the other.
Okay, but what if you have a mixture of different colors, like a blob of black ink? For this, we use paper chromatography. It's so cool. You put a little dot of ink near the bottom of a strip of filter paper and then dip just the very bottom edge into some water. As the water slowly creeps up the paper through capillary action, it passes right through that ink dot. Now, that black ink is actually a secret mixture of different hidden dyes. Some of those dyes interact heavily with the water, so they get dragged all the way up to the top. Other dyes interact more with the paper, so they get left behind near the bottom. As the water travels vertically, the black ink literally stretches out into a beautiful rainbow, separating every single hidden color perfectly.
Moving on to Section 4, separating heterogeneous liquids, untangling the messy stuff.
Let's talk about oil and water. They are completely immiscible. They absolutely hate each other. If you shake them up, they're just going to separate right back out. So we just let gravity do the heavy lifting for us by using what's called a separating funnel. We pour the messy mixture in and just wait. The heavier water settles down to the bottom, and the lighter oil floats nicely on top. Now, right at the bottom of this funnel is a stopcock, which is basically just a tiny tap. You just open the tap, let the water drain out into a beaker beneath it, and the exact second the oil layer reaches the bottom, you close the tap. It is incredibly simple and incredibly effective.
But sometimes heterogeneous mixtures are just a bit more stubborn. Take blood or really cloudy, muddy water that just refuses to settle. For this, we bring in centrifugation. We put the mixture in a tube and spin it around at ridiculously high speeds. That intense outward centrifugal force shoves all the heavy particles down to the very bottom, leaving the nice, clear liquid sitting on top. Alternatively, for that stubborn, muddy water, we can use coagulation. We drop in a chemical called alum, also known as Fitkari. The alum basically acts like a magnet, forcing all those tiny, annoying, floaty mud particles to clump together. Once they form a heavy enough clump, they drop straight to the bottom, and you can just pour off the perfectly clean water.
Finally, Section 5, the sublimation shortcut, skipping the liquid phase entirely.
Now, normally, matter goes from solid to liquid and then to gas, right? But some very special substances skip the liquid phase completely. When you heat them, they go straight from a solid to a gas. A neat little trick called sublimation. And when you cool that gas down, it goes straight back to being a solid, which is called deposition.
So let's say you accidentally spill some sand into a jar of camphor, or kapur, which is a solid that sublimates. How in the world do you unmix two solids? Well, you place the mixture in a dish and put an inverted glass funnel right over the top. Then you turn on the heat. The sand, it couldn't care less about the heat. It just sits there. But the camphor instantly sublimates, turning right into a gas. That camphor vapor floats up into the funnel, but remember, the top of the funnel is cool. So, the split second the vapor hits that cool glass, it undergoes deposition. It instantly turns right back into solid white camphor crystals clinging to the glass, leaving the boring old sand sitting all by itself in the hot dish below. Problem solved. And there you have it. From simple heating and cooling to exploiting physical states and boiling points, science gives us this absolutely amazing toolkit to untangle the physical world. So I'm going to leave you with this final thought today. The next time you look at your morning coffee, or the ink in your pen, or just take a breath of air, knowing what you know now about how all these elements combine and pull apart, what invisible mixtures are waiting to be separated right in front of you. Think about it. Thank you so much for exploring this topic with me on today's Explainer. Keep learning, keep asking questions, and I'll catch you next time.